a week from Monday. How many more sections do we have? Just 3 more sections.
Oh, just 3.
Today we're doing 2. Today we're doing 2. After today, there's only 1 more section. You should be doing a, what's the word, boatload of work over the weekend. Boatload.
Yes. I have it all on my nice to-do list.
your
It's like
to-do.
all math.
Make sure you check it off.
Yes, that's
sure
the
you
best
do it.
part, man. That's the best
know, that
part.
is the best
Crossing
part.
things off the list.
I know.
Don't wait until next weekend.
I can take the exam.
Haley's.
Yeah. Yeah, we'll talk about it.
No, I can be here. I'll be here for the exam.
You're going to do it in class?
Yeah, my daughter's dad comes by.
Oh, okay.
So I will,
Awesome.
yeah, I can
All right.
study over the weekend.
Yeah, great. Excellent.
Yay.
You can eat, that's fine. You're more than welcome. You can eat.
Separation.
All right, so we're covering 2 sections today. Let's go. Here we go. So
Here we go.
here we go. Oh, it's a good thing we have 2 hours and 15 minutes of math. So we are going to talk about the tangent plane first. And the tangent plane is analogous to the tangent line. And so the idea behind the tangent plane is that it's the best linear approximation to a surface. So if the surface is differentiable, you could zoom way in, and it would look like a plane if it was differentiable. So the tangent plane is we think of it as the best linear approximation to the surface. And the tangent plane is essentially the collection of all tangent lines to all curves that pass through the point of tangency. So if you imagine every possible curve that goes through that point, and then collect all the tangent lines, those would form the tangent plane. It's a big tangent line bundle. Well, there's some math for you. Tangent line bundle. Okay, so intuitively again, surface is differentiable if it has a unique tangent plane. The tip of a cone obviously is a surface that would not be differentiable because there's not a unique tangent plane. So it's got to be smooth. And what we have to do is find the equation of the tangent plane. And the way that we have been finding planes, and the way that we will continue to find planes, is that we will use this formula, n dot v equals 0. So n dot v equals 0. That gives us the equation of the tangent plane. We have to find n, which is normal to the surface at the point. And then we have to find v. V is just a regular old displacement vector. V is just x minus a, y minus b, z minus c. So n dot v, where v is a general displacement vector off a point that you know is in the plane. So you have to know one point in the plane, and you have to know the normal vector. And you're golden. So this is another interpretation here. Last time we talked about surfaces that were defined, what does that mean? Surfaces that were defined implicitly. And surfaces that are defined implicitly, what we can do is create this function cap f. And cap f is going to then have a gradient that's perpendicular to its level surfaces.
Okay, say that again.
Yeah, I'll say it at least 3 times. Okay. So if we have a curve defined implicitly, then we have a gradient that is orthogonal to its level curves. So everyone follow that? Let me do some writing on the board. So let's suppose we have a curve that's defined implicitly. For example, let's suppose we have something like x squared plus y squared equals 1. So that's a curve, and it's not a function, but there are 2 functions implicitly defined with that relation. And so what we can do is define a function capital F such that the curve that we started with is a level curve to the function capital F. So we sort of build this parent function that has the original curve as a level curve. And then if we take the gradient of this parent function, the gradient is going to be orthogonal to the parent function's level curves, well, this is one of the level curves for this capital F. So this then acts like a normal vector. And we could cancel out the 2, because if we're only interested in a normal vector, the length of the vector doesn't matter. So we could scale this down. That will be normal to the curve. So if we have an implicitly defined function, we can create a parent function with a gradient orthogonal to the original curve. So gradients are always orthogonal to level objects. What do I mean by that? Let's suppose we have a surface that is defined implicitly. So now we have a sphere of radius 1. If we wanted a normal vector to that sphere, we could do the same thing. We could build a parent function. So we could say, hey, let's create this parent function. The graph of that parent function is in 4-dimensional space. We have no idea what it looks like. But we do know what its level surfaces look like. If we were to plug in constant values for capital F, we would get level surfaces. So up here we have a level curve for cap F. Here we have a level surface. Level surface for cap F. That makes sense? So gradients are always orthogonal to level objects. So if we have a curve in 2-dimensional space, we build the parent function. That would actually be a surface in 3-dimensional space. Its gradient will then be perpendicular to the 2-dimensional level curves. If we have a surface, we build a parent function, which is a 4-variable object. Don't know what it looks like, but its level objects, which are surfaces, will have del F as a normal vector. So we can come over here and find del F. Del F would be 2x, 2y, 2z. That's normal to the level surface. We could scale this down because there's no point in having that extra factor of 2. So that would be a normal vector to the original surface. Will?
Do we ever get into the 5th dimension in this class?
No. Next class.
Just 4.
Linear algebra. Linear algebra, you get into the nth dimension.
There's no numbers left in any of the math.
Yeah, there's no numbers left.
So you're given like a
12 dimensions, I think.
Parent.
and then
Take its gradient.
take the gradient of that, which is normal to the original equation you were given?
Yes.
Okay.
Yeah.
Sorry,
Exactly.
I was like
No,
trying to
that's
make sure I
exactly
figured out
it.
what.
So if you start with a curve, you build a gradient, you build a surface, its gradient is perpendicular to the curve. So if you start with a surface, you build they call it a hypersurface. The gradient to the hypersurface is orthogonal to the surface.
Okay.
Yep. Go up 1 dimension, take the gradient, come back down, and you have an orthogonal vector. Up 1 dimension, take the gradient, come back down, and you have a normal. So, and that keeps on going. If you had an object living in 4-dimensional space, you would go up to 5-dimensional space, take the gradient, and that would be orthogonal to your object in 4-dimensional space. Can't visualize it, but that would work. It would be true. All right, so here they're just showing the analogy with which we just went through. Here's the level curve analogy. Here's the level surface analogy. Well, I guess the level curve analogy for the level surface definition. Okay, so this is what we just said. We just said let the surface be defined implicitly. So for an implicitly defined surface, we're thinking capital F equals 0. So we're just thinking the same exact example I just put on the board. X squared plus y squared plus z squared equals 1. So that's a surface. It's got implicitly defined functions in it. So we're going to use capital F as the parent function, the hypersurface, if you will. We take the gradient of the hypersurface, and that will be orthogonal to the surface. We dot it with the displacement vector on the surface. That will give us the equation of the tangent plane. So let's do it.
Can you say that one more time?
Yeah.
no.
So we have a surface that's defined implicitly. So that means that it's a relation and not a function, like a sphere. A sphere is a relation, not a function. But it does have two implicitly defined hemispheres. Each of the hemispheres is a function. So a sphere has two implicitly defined surfaces, the upper hemisphere and the lower hemisphere. We're going to build this hypersurface. We're going up one dimension. And that capital F is a hypersurface to our surface. It's one dimension out. Just like a surface is the parent function of a level curve, of a curve. So if we have a curve that's not a function, like a circle, we build a surface, and the gradient of the surface is orthogonal to the curve. Here we have a surface. It's defined implicitly, though, so we can't just find a normal to it. It's defined implicitly. So we build up to the hypersurface level, take the gradient there, and then that will be orthogonal to our surface. So this right here, think of the sphere. Think of the unit sphere. Think of this as x squared plus y. You always need some sort of example that sort of ties it all together. So if you had that, so this is a unit sphere, and I just pulled the 1 over so that I could think of it as capital F equals 0. All right, so that's what capital F is. Capital F is this parent function. It's a function of 3 variables, which is a hypersurface. If you were to graph W equals capital F of x, y, z, that would be a surface in 4-dimensional space, which they call a hypersurface. So then the gradient of capital F, the gradient of this hypersurface, will be a normal vector to the implicitly defined surfaces that are inside here. So if we're thinking the sphere, then when we take del capital F, that's going to create a normal vector that's anywhere on our surface, anywhere on the sphere, on either of those implicitly defined surfaces. And then our displacement vector, same as it ever was, right there. So this is just n dot v is equal to 0. Nothing has changed. We have n dot v equals 0. So the question is just, how do we find n? And this is the way we find n. We've got an implicitly defined surface, build a parent function, take its gradient, and that's n. Yeah?
Okay, I think you just said this, but I
Yes,
just want to
okay.
make sure x minus a, y minus b, z minus c, that's still our direction vector v, right?
Yep, that's our direction vector v.
Okay.
So ABC, so if we imagine a general surface in 3-dimensional space, ABC is the point on the surface. And then XYZ is a point in the tangent plane. So we're imagining that tangent plane. Let's see. So we have a tangent plane somewhere sitting on there. And XYZ is just a generic point in the tangent plane. So this is in the tangent plane. That's XYZ. So if you form this vector right there, that's x minus a, y minus b, z minus c. Shazam. Yeah. So let's do it. So here we have a surface. It's not a function because we can't, although maybe this one we actually could isolate z. So you might be able to write this as a function. But we're just going to think generally. We're just going to think, okay, it's a surface. If it's a surface, let's create a parent function whose graph would be a hypersurface. Do we need to put the constant in? No. We don't need the constant. Because as soon as we start partialing, constants vanish. So f you can think of as a hypersurface or as a parent function to the surface that we began with. Either way. And del f is going to be partial with respect to x gives us y plus z. Partial with respect to y gives us x plus z. Partial with respect to z gives us x plus y. This is normal to the surface. It's not normal to the hypersurface, but it's normal to the surface. Right, the gradient of the hypersurface is normal to the surface. Question?
So you said that it would be in four-dimensional space, but since we just took the constant out because we don't really need it anyhow, that's just what we're looking for, right?
Well, if you were to graph capital F, that would be in four-dimensional space with or without the constant. The graph of capital F is in four-dimensional space. Just like if we have the curve x squared plus y, if we have a unit circle, x squared plus y squared equals 1, right? That curve is in two-dimensional space. But if we then build this parent function, this is in three-dimensional space. This is really z equals x squared plus y squared, which is a paraboloid in three-dimensional space. So when we create the parent function, we've added one extra dimension. So capital F, or z, in two-dimensional space, we let z equal the dependent variable. In three-dimensional space, typically we'd use a w if we were looking for a lowercase dependent variable. But z equals x squared plus y squared is now in 3 dimensions. So when you get a parent function to a curve, that's a surface. A parent function to a surface is a hypersurface. Gradient of hypersurface is orthogonal to surface. Gradient of surface is orthogonal to curve. So this parent function or parent function or surface. Gradient here will be orthogonal to those level curves. So we're essentially trying to create a parent function that we can take the gradient of, because the gradient will then be perpendicular to the curve or surface that we started at. So then the equation of the tangent plane. The tangent plane's equation is just the gradient and the direction vector dotted together. That's it? Party.
Thanks.
So we're going to do n dot v equals 0. And n for us at this point, let's figure out what the n is at that particular point. So the n at that particular point looks like it's going to be 4, 4, 4. Now we could scale it down to 1, 1, 1 if we're just looking for any old normal vector. We could use 1, 1, 1. So this is del f evaluated at this point. So I'm plugging in 2 for each of the x, y, and z's, adding them together. And then our displacement vector is x minus 2, y minus 2, z minus 2. And we set all that equal to 0. So there's our plane. So parent function gradient, substitute the point to get the particular normal. This is normal at every point on the surface, so we want to find the particular normal at that point on the surface.
Do you not need to
Whoa, 3 hands just went up. This is so unusual. Let's start in the back.
So could you just, instead of plugging in the points right away, could you just take the gradient function that you found and dot that with your displacement vector and then plug in a point afterwards?
Yep.
Okay.
Yep.
Cool.
You definitely could do that. The only issue, I should put a caveat there though, is that you want to make sure this xyz is different than this xyz. These xyz's are xyz's on the surface. These xyz's are on the tangent plane. So you just have to be careful. So if you were going to do that, you probably want to put x naught, y naught, z naught, so that you know that it's different than the variable xyz. Omar?
So you wouldn't make a vector out of those 2 points and then put that vector in for x, y, z?
This point is just a different point on the surface. They're saying find the so
2 planes, 2 equations.
2 planes, 2 equations.
Okay.
Yeah. So they're not saying that those points are connected in any way. It's just 2 different problems, part A and part B. Yeah. Well,
Yeah, I'm a little confused about how you got from your normal vector y plus z, x plus z, and x plus y over 4, 4, 4.
how we went from here to here?
Oh,
I plus 2.
2 plus 2.
Oh, okay, and you gain those 2's from
Yes,
that.
exactly. So we're taking these and we're plugging them into, those guys. So we found the normal vector in general, and now we're just going to figure it out at that particular point.
And then where'd you get the x minus 2, y minus 2?
So that x comma y comma z is a random point in the plane, and then 2, 2, 2 is a point on the surface that's also in the plane. So that's our point of tangency. So 2, 2, 2 is this ABC right there. It's the point of tangency. So x minus 2, y minus 2, z minus 2 is that general displacement vector that's in the plane that we then dot with n.
So I'm noticing, like, with the tangent planes and tangent lines, the only time the x's actually show up in the direction vector is if we're finding the equation of a plane of some sort. Is that accurate? Because when we're finding tangent lines, there's no x in the direction, x, y, z in the direction vector.
There is an x minus a and a y minus b.
Right, but there's no physical, like, it has to be a plane for the x's to be present in the direction vector, right?
But when we look at this for a tangent line, we're thinking of this scenario. There's our tangent line. This point is a comma b, and x comma y is a general point on that line. So x minus a, y minus b is this vector.
Sure.
So we will be left with an x and a y in the equation. So when we end up with the tangent line, we're going to have like y equals mx plus b or ax plus by plus equals c.
Okay. Sure.
We'll look at it. We can look at an example of that. Okay, so let's finish this one off. All we have to do here is dot these together. We can divide by 4. Can we divide by 4 right now? We divide both sides by 4. We either divide by 4 now or divide by 4 later, because we want to divide out any constant factor that is shared between all the terms. So let's divide it out now. So here's our equation. X minus 2 plus y minus 2 plus z minus 2 is equal to 0. So our final form would be x plus y plus z is equal to 6.
Does that not have to all be over 4 or no?
Yeah, I was about to ask that.
Oh, no, we divided by 4.
But you didn't divide your x minus 2, y minus 2, z minus 2 by 4. Why not?
So because let me see if I can. So let's do it. Let's talk about it in 2 ways. So if you imagine this 4 being multiplied across, it would be 4x minus 8. But when you divide 4x minus 8 by 4,
Oh, I see.
you're going to get back to x minus 2. So you can think of it that way, or you can think of it this way. If you had 4 times 5 in the numerator, and I have a division by 4, do I divide it into both?
No.
Right? We just divide it into 1. So we're just taking the 4 and we're dividing it into 1 side of the product.
Right.
Does that make sense?
Could you have just like scaled the normal vector to begin with?
Yes. And that's essentially what we just did. Yeah, exactly. So because you get a 4, 4, 4, that's the normal. Any normal works. Any normal is going to give you the same equation. So if you see that there's a common factor in your normal, you can just cancel it out right away. So if your normal is 2, 4, 6, make it 1, 2, 3. Right? And then you don't have to divide in the end.
Are you going to do part B or no?
No.
Okay.
So let's go to the next one. So here, first off, do we know what that surface is?
Yes.
Oh, good. What is it?
Something.
It's a quadric surface.
We know collectively, but not all of
Okay.
us individually know.
So if you cancel out the z, what do you get?
It's an elliptic cone.
So if you cancel out the z, you don't get an ellipse, you get a point.
Circle.
It's elliptic.
Not a
X squared
circle.
plus y squared equals 0.
X squared plus y squared equals 0 is just a point. So so we get a point. Let's cross out y. We get
Another point.
no. No.
You get y squared, or
You
x
get-
squared equals z squared.
X squared equals z squared, which is x equals plus or minus z, or
Which
z
is a
equals plus or
line.
minus x. So you get the 2 lines.
Oh,
You get
the
the
two
x.
Oh, yeah.
Right? get an x. Cross out that one, you get an x also. You get y equals plus or minus z, or z equals plus or minus y.
Oh, plus or minus.
So you have two x's and a dot. That's what you end up with. Two x's and a dot. So your level curves are that, or not your level curves, your traces are that. So you have a cone.
It's
Okay.
just a cone? Just two cones?
We call that one cone. One cone with two sides.
We call that
I don't think I have.
They're like pointed.
The cones your whole life are really half cones. But you never knew. So those things that you've been dealing with all along, that's really a half cone. Sorry. So yeah, when we think of cones from here on out, it's two-sided.
We just accept.
If you're talking about the quadric surface, it's a two-sided thing.
It's terrible.
Okay, it's terrible. It's worse than terrible. All right, so let's go ahead and build our parent function. The graph of our parent function, if we were capable of graphing it, would be in four-dimensional space. It would be a hypersurface. The gradient of this parent function is going to give us, whoops, not a plus, but a comma. The gradient of this parent function is going to give us a normal. So here, maybe it's more intuitive to scale right here before we go on. So if we scale right here, let's ditch a factor of 2. So we're just shrinking the length of that normal vector by a factor of 2. So that is normal to anywhere on this cone. That's normal. We're going to just do this first one. We want to be normal to that point. So the normal at that point, so maybe I'll put of 3, 4, 5 just to emphasize that it's the normal at that point. We plug in the 3 for the x, plug in the 4 for the y, plug in 5 for the z. So that's a normal at 3, 4, 5. So 3, 4, 5 is on this cone. That vector is normal to it. Now we want the tangent plane there. So the tangent plane, the TP, is n dot v equals 0. And that is going to be 3, 4, negative 5 times a general displacement vector off the point of tangency. The general point on the tangent plane is x, y, z. So we have an x, a y, and a z. That's a general point on the tangent plane, and we're going to displace off of our point of tangency. Our point of tangency is 3, 4, 5. So we're going to have x minus 3, y minus 4, z minus 5.
Plus
Oh yeah, there's a plus somewhere.
z plus 5.
No.
No.
That's our point.
Oh, never mind.
Yeah, it looks a little funny because our normal vector is looking a lot like our point. Silly.
Never mind.
Okay, so we dot those together. And can we do this all at once? Can we do 3x plus 4y minus 5z? So there's the left-hand side. And then we do the constants. We're going to get minus 9, minus 16, which is minus 25.
It's just 0.
Plus, oh yeah, it's just 0. Thank you. So that is our tangent plane at the point 3, 4, 5.
So it's just tangent at that point.
Well, on a cone, because a cone has a slanted edge, it's actually going to be tangent along a whole line,
Oh.
right?
But like on a this kind of a surface.
Then it would just have one
it would
point of
just be
tangency.
tangent at one
Yeah.
point. Okay.
And the point in the middle, would that just be, would that be undefined? Can you
There
find
would
that?
not be a unique tangent plane at that vertex point, so we would say it's not differentiable at that point, which means there's no tangent plane, no unique tangent plane.
So what are we using the -4, -3, 5.4?
Did you say 3, 4, negative 5?
Well, it says x plus y minus z squared, 3, 4, 5, and -4, -3.
Oh, so this is just to find another tangent plane at this point.
Okay.
It's just a second, it's part B. So it's saying first find the tangent plane at 3, 4, 5, and then find another tangent plane at -4, -3, 5. Yeah, so
I was reading that as
yeah, it's not.
tangent
Yeah,
plane
that's
pass through those.
right. Yeah, it's two separate problems.
Oh.
Two separate problems.
I have a question.
Yeah.
So just because like we ended up with 3x plus 4y minus 5z, because our normal was just x, y, z anyways, like would we have been able to just like, go, I mean, can we just go straight to that? Because you can see that you're going to cancel out.
You can, oh, in that case, yeah, and that's very rare, but yeah, in this case, you see that the
Yeah.
5 and the negative 5 are,
Yeah.
you know, combined. Yeah, that's an anomaly. It's a wrinkle. Okay, now here, we now know a way to find the tangent plane. Okay, so we have a way to find the tangent plane if we're given a surface implicitly. If we are given the surface explicitly, we can just pretend it's given to us implicitly and do what we just did and not worry about it. Or you can remember a slightly different but closely related formula. Totally up to you. Totally up to you. Do you want to remember a new formula? If the answer is yes, then there's one. There's a great one. Remember that one. If you don't want to remember a new formula, don't do it. Because the way that we just did it in the last two examples works perfectly here. So let's talk about this. So if we were given this surface explicitly, so z is a function of f, we could just build our parent function by saying capital F is going to be little f minus z, or z minus little f, doesn't matter. And let's do what we just did a few minutes ago. Let's figure out the gradient of capital F. So the gradient of capital F, bless you, is the partial with respect to x of the right-hand side. So that's going to be f sub x, comma. Right? The partial of the right-hand side with respect to x is really just the partial of this with respect to x. That's a z. There's no x's there. That's the independent variable z. There's no x's hidden inside of there. It's just an independent variable. So there's no more x's that you can find inside that z because it's just a variable. And then we have f sub y. And then what's the partial of this right-hand side with respect to z? Negative 1. Right? That variable z, the coefficient is negative 1. There's our normal vector. That's it. So n can equal f sub x, f sub y, negative 1. Or if you wanted, if it's more convenient in certain cases, you could multiply by negative 1 and do that. So that is normal to the surface z equals f of xy. Notice that if we want to build that equation up there, it's very simple. If we want to build the equation that they have up there, notice this. So what do? We do n dot v equals 0. So n dot v is 0. So we're going to take n, f sub x, f sub y, negative 1. We need to dot it with a displacement vector. So that displacement vector is going to be x minus a, y minus b, z minus f of ab equals 0.
That was unexpected. Can you explain that?
I can.
Will you explain that?
Yes. So AB, isn't AB down in the xy plane?
Yes.
So the z coordinate, instead of an ABC, we already have exactly what the z values are because we're given our z's explicitly. Z equals f of xy, so if we plug an a and a b in there, we get the z value. We get the c. So it is just c, but we know what it is because we know what that, we have that function defined explicitly there. So then we dot this all out and solve for z, and we get this. So that dotted with that dotted with that. Now negative 1 dotted with this gives a negative z plus f of ab, and then we add z to this side. And so now we've written the tangent plane. See, the big difference is here the function is given explicitly. That means that you can give the tangent plane explicitly, which means you can solve for z. With some of our other ones, you may not. We wrote the tangent plane in this or in this general form for both of these. Now, both of these you could solve for z. There's times, though, that maybe you don't want to because the general form is just, sometimes we like the general form because you can see the normal vector. Normal vector is 1, 1, 1. That's very convenient. General form here, we see the normal vector. Over here, if we write it in this form, the normal vector is not jumping out at us. But you can solve it for z. And there's applications where we will solve for z, where that's a better form than having it in ax plus by plus cz equals d form. It's just going to depend. And we'll know, it'll be clear. So let's go ahead and find tangent plane here. So tangent plane, again, we can either memorize a new formula or we can just do it the way we already did it, which doesn't matter to me. So I think it's more intuitive just to stick with what you've got. So if we want to write capital F, the parent function, we can forget about that constant. And let's just subtract the z to the right-hand side. So there's a parent function. That's a hypersurface. The gradient of that hypersurface will be normal to the original surface. So del f is 4x comma y comma -1. Now, one pattern that you're not going to be able to not observe, you will see it, and you're going to be like, oh, wait, I know the normal vector immediately without even writing capital F. And it's going to be, and maybe I should write it with a z, little z, just so it's maybe a little bit more obvious. Right? So there's our z. Z sub x is right there. Z sub y is right there, -1. So that's always going to be normal if you're given a surface explicitly. It's always going to be that case. Okay, so there's our normal vector. So our plane, we're going to think of our plane as n dot v equals 0. So the normal vector at the point of interest. So again, let's just do the first one. They've asked us to build 2 tangent planes. Let's just build 1. So n at our point of interest. So we're looking here. We're plugging in -1/2 for x. So we get -2. Plugging in 1 for y. Plugging in, doesn't matter. -1 is our z value always. Dot general displacement vector off of that point. So x plus 1/2. Y minus 1, and z minus 3. And that all has to equal 0. So that'll give it to us. This is our tangent plane. So we get -2x plus 1/2 plus y minus 1 minus z plus 3 equals 0.
How is that not plus 1?
Did I skip a 1 somewhere?
Minus 1 rather.
Yeah, you should have
Next to it.
-2x minus 1.
-2x minus, oh, thank you. I see it, I see it. I see it. Minus 1. Okay, so we can either write this in general form, and if we write it in general form, let's do it one step at a time. We'll put all the letters together, and then what do we get? Just a +1 on the left, so that's going to be a -1 on the right. And we always want our leading coefficient to be positive, ideally. So we would multiply through by -1. So that's the tangent plane written in general form. Now, they gave us the original surface explicitly. So in my math lab, they may say, oh, write your tangent plane explicitly. So if they say that, you would write it that way. So either way, on a test, it does not matter. They are both the same plane. Either way.
Ross,
Yes?
what is, I don't get this, the note. I don't understand what was said.
So the note is, we built our parent function,
Sure.
and we took its gradient.
Okay.
And the note is that, hey, if you look at your original explicit surface, the first component of our normal vector is z sub x. The second component is z sub y. And the third component is -1. So once you've done this a bunch, you may just come down and write this immediately and equals, and not even write those two steps. So you may get to that point where it's like, oh, I know what's going to happen when I have an explicit function. I know that it's going to be z sub x, z sub y, -1.
Okay, I see it.
Right? It's always going to be that. Let's observe it in the next problem. So when we look at this one, if we build the parent function by subtracting z, and let's just ditch the 2 there, then our gradient is going to be, we partial it with respect to x, and we're going to get y cosine xy. And then partial it with respect to y, we're going to get x cosine xy. Partial it with respect to z. And then let's just make that observation. That's, bless you. That is z sub x, that is z sub y, and that is -1. So it will always be that way. And now we're going to just find the normal. We're just going to do one of these planes. Let's just do that one. So the normal vector at 1, 0, 2, plug in 1 for x, 0 for y. Cosine of 0 is 1. Yeah, it looks like that's going to end up being 0 anyway, since y is 0. And the normal vector here, or the component here, cosine of 0 is 1. So we're going to end up with 1. So there is the normal vector that we'll use. So we're going to take that normal vector. We're going to dot it with a general displacement vector off of that point. So general displacement vector would be this. So there's our tangent plane. Just have to multiply it out. So we end up with y minus z plus 2 equals 0. So if you wrote it in general form, it would look like this. If you wrote it in explicit form, it would look like this. Either are totally correct. Any questions? Starting to feel easier?
Why did the sine and cosine disappear?
Well, here we're taking the derivative of sine, so we're getting cosine. But then down here, we're evaluating our point. So x times y is 0. So here, cosine of 0 is 1, but then 1 times 0 is 0. And then over here, we have 1 times 1, which is 1.
Okay.
So we're just evaluating at that ordered triple. Other questions? All right. We're off to our next exciting concept, linear approximations. Oh, how about using the tangent plane? Great idea. The tangent plane is the best linear approximation to the surface. So we've already done this. This is just the tangent plane. This is just the tangent plane written in explicit form. That's all it is. Tangent plane in explicit form. Nothing more, nothing less. Tangent plane in explicit form. And if you want, just keep doing what we've been doing. Parent function, take the gradient, dot it with v, solve for z, and that's going to be the linear approximation. The linear approximation is the tangent plane.
So how we could find linear approximations, quadratic, cubic, whatever approximations with like Taylor series and stuff. Is there a way to generalize it with Calc 3 as well, or?
Well, that's what the Taylor series is. The Taylor series, you can use a Taylor series where you have more than one variable, and you can do the same exact thing. So you can have a tangent plane and then a paraboloid and then,
So we could theoretically do this, but with Taylor as well?
yeah. Yeah, we won't do that though. That's really complicated.
Do we
Very
do we use
complicated.
Taylor series at all in Calc 3?
No.
Oh, good. That's good.
You'll use them in differential equations though.
No idea.
Well, I don't have to remember them yet.
You don't have to remember them yet. Taylor series, just think of it as an infinite polynomial. Why would you ever want a polynomial? Because they're easy to differentiate and they're easy to integrate.
Taylor series for science.
And they're easy to program into computers.
Oh, those were the ones we had to memorize, right?
Yeah.
Summation.
Yeah.
1 plus.
K equals 0.
When I've got my own engineering firm, I'm just gonna have a big laminated sheet of them on the wall. And
The important Taylor series.
Profit.
I still remember.
I mean, the one thing when you get into engineering courses, so the Taylor series were infinite polynomials, which are easy to handle, but in engineering, quite frequently you use a Fourier series instead of a Taylor series. So a Fourier series will write all functions as infinite sums of sines and cosines, which is remarkable. So what that allows you to do, if you have a discontinuous function, like a step function, you can actually model that almost perfectly with a Fourier series. Why would you want to model a discontinuous function with a continuous function? Because you can take the derivative. If you have a step function, you can't take the derivative. It's discontinuous. It's not differentiable. But if you can approximate it with a Fourier series, which is continuous and differentiable everywhere, then you can do some amazing things. So you'll typically in engineering you'll use those instead of traditional Taylor series. Okay, so this is one observation here. So this is the linear approximation. There's going to be two types of applications that we talk about. One is going to be find the linear approximation for blah, blah, blah. And another one is going to be talking about the change in the function values. And we're going to look at something called percent change. And when you do percent change, you need the differential and not the linear approximation. But to get to the differential, to get to dz, all we're doing is subtracting f of a, b from both sides. So z, so if we take that linear approximation, let's replace this with a z for now. So if we move this over to the left, then we have f sub x times x minus a plus f sub y times x minus times y minus b. So we got that. This right here, remember that this is the tangent plane up there. So the x's, the y's, and the z's are on the plane. They're not on the surface. So those are on the tangent plane. Okay? So this right here is going to be, we can replace this, and you can think of this right here. If that z is on the tangent plane, then this is going to be a dz as opposed to a delta z. So that z is on the tangent plane. So it's a dz, not a delta z. Let's see if I can convince you of what the differences are. So we'll go back up there and you can look at that in a second, but let's just talk about this first. Let's take a look in one variable calc for a moment, because this is analogous to one variable calculus. And in one variable calculus, it's a little easier to draw and understand the drawing. So let's just do that. So in one variable calculus, your situation looked like this. There's your tangent line and our point of tangency. And then we come over here, and we have two things. Actually, let me use it's too messy. Let's use the dot tool. So you have two things. You had dy and you have delta y. So when you look at this little triangle here, this is the differential triangle. The differential triangle is coming from the tangent line. And that's where your d, in this case, 2 dimensions, that's your dy. Your delta y is the actual change in the function. So delta always means exact change along the function. So delta y, delta is d for difference. It is the true difference in y. The little d means the difference along your linear approximation. The little d means the distance along the difference along the tangent line. So dy is this piece, delta y is that piece. Same thing with the surface here. If we can look at this. dz is this distance right here. That's a difference in z values on the tangent plane versus a difference in z values along the surface. So dz is measuring a vertical change along the tangent plane, whereas delta z is measuring a vertical change along the surface itself. Analogous to what you did in Calc 1 right here, and the idea was very simple. If this was your x, and in Calc 1 they usually call this x plus h, as h goes to 0, or x plus delta x, sometimes they call it that. Either way, doesn't really matter. So as delta x goes to 0 here, that forces dy and delta y to be really, really similar, close. They're good. Dy is a good approximation for the delta y. So same idea up here is what we're getting at. So up here, this z, the x, y's, and z's are on the tangent plane, just like down here, when we write the equation of that tangent line, the x's and the y's are on that line. And so dz is going to be an approximation for the actual change in the surface values. So delta z is the true change in surface values. dz is an approximation along the tangent plane. So there are going to be times, applications, where we're curious about percent error, and that's where we're going to use the differential. Coming soon to a slide near you. Okay. All right. There's a lot of writing here. Don't write any of it down. So this is just words for what I just said. Right here, delta z, it's the true change along the surface. That's the change along the surface. That's what delta z is. So it's taking the change in two function values on the surface. So it's an exact change. The linear approximation, we just looked at. This right here is the change along the tangent line. So that's dz, the change along the tangent line. That's what we just talked about. So, but, long story short, it's either you take the tangent plane, which is the L, that's the tangent plane. All you do to get down to your dz, all you do is get rid of the f over here, the f of AB. That comes over to L to create this difference. So dz is just this part. So the dz is just f sub x, x minus a, plus f sub y, y minus b. It's just the differential part. So that's what we just talked about. The differential in z is f sub x dx plus f sub y dy. You can think of that as a dot product if you want. It's really the gradient dotted with a vector differential. And you can think of the vector differential as dx comma dy, dx comma dy, dotted with the gradient. All right, so let's do one of these. So here, so we have to decide when we want the linear approximation and when we want the differential approximation. Usually it's pretty obvious. They're telling us here, use a linear approximation. So that just says, use the tangent plane to approximate the value of the function. So we're going to do that. Let's do it. We know how to do that. So let's build the tangent plane and solve for z. We write the tangent plane explicitly, then that z equals, that's approximating along the tangent plane. So normal vector, bless you, will be minus 8x minus 16y, negative 1. And you can build that hypersurface in your head, or just get to the point where it's like, oh yeah, it's always going to be f sub x, f sub y, negative 1 when you have an explicit surface, an explicit function. So normal vector at our point of interest normal vector at negative 1, 4. Plug in negative 1 for x. We get 8. Plug in 4 for y. That is the normal vector, or a normal vector. The normal vector that we will use. So now the equation of the plane. So again, let's just keep it simple. We'll take our normal vector and we'll dot it with the general displacement vector instead of remembering another formula. Just it's very easy to get tangled up in all that stuff, all those different combinations. If you do it the same way every time and solve for z, it works. Okay, so one issue here though, our point on the surface. So we know negative 1 is the x value. We know 4 is the y value. So what is it for the z value? What do I write? Z minus what?
0.
So if we're only given a and b,
F of negative 1.
right, so we'll plug it into the function. So if we plug into the function negative 1 comma 4 into the function to get the z value, so that's going to be negative 1 there, positive 4 there. So negative 1 in there is going to give us 8 minus 8 times 16, looks like. So that's going to be 8 times negative 15. That's going to be negative 400, no, negative, what, 120? Multiplying's hard. Is that right?
Yes.
Okay, 60 twice.
So the z component of v would be z plus 120.
Z plus 120, right there.
X plus y.
And it's going to be x minus a minus 1, so plus 1. Thank you. Minus minus 1. Yes.
Oh, so we plug it into the normal vector, we'll plug it into the original equation.
To figure out what the z value is, we plug those two into the original equation to get what the c value is, to get ABC. Right? So I plugged in negative 1 here. So I skipped the 12 minus 8 step.
Yeah,
or
yeah,
12
I
minus.
was like, where'd the 12 go?
12 minus 4.
Yeah.
12 minus 4 is 8. Yeah, sorry. Okay, so then our tangent plane, 8x minus 64y. I'll just focus on these guys first, then we'll do all the constants at once. So then we have 8, and then minus 64 times minus 4, so that's plus 128 twice, 2.6. And then minus 120 equals 0. So we have 8x minus 64y minus z. Let's just combine all these constants. So
It's 144.
144 total, thank you. Okay. So that's our tangent plane. It's not even, I didn't write it in general form yet. We don't have to write it in general form here. So they want us to estimate that. So what I'm going to do is write the tangent plane as a function. So I'm going to solve for z. So z will equal, if we just add z to the other side, we get 8x minus 64y plus 144. So this is our linear approximation. That's L. So we just equation a tangent plane, solve for z. That's the linear approximation. So now it says estimate f of that. So obviously this is kind of kooky because you could just plug it in here easy enough. We have calculators. You know, this is a pretty simple function. But the idea conceptually is that, okay, let's plug this into the tangent plane, and we should get a z value that's pretty darn close to this because we're just a smidge away from negative 1 comma 4. So we're going to get our approximation. So z of negative 105 comma 3.95. So plug that in and tell me what you get. So what do you get when you plug it into that tangent line? Tangent plane.
Negative 117.2 exactly.
Negative 117.2. Great. Now let's plug it into the function just to see. We should be really darn close. So, and we have technology, so you can plug this into the function easily enough. So what do we get when we plug that in? I assume a negative number. Negative
Hope so.
117 point something, hopefully 0.1 or 0.3 or 0.2 something.
Yeah, negative 117.23.
0.23?
Exactly.
Yeah. So we see that the tangent line approximation value is super close to the actual value. Obviously, in a case like this where it's simple enough to plug it into the original function, doesn't matter. But if you're dealing with massive powers of x and y and combinations of them, having the tangent plane, as long as you're close to, as long as your point that you're trying to approximate is close to this point, tangent plane is going to be a heck of a lot easier to find that value. So if you're programming something with huge massive numbers, it's going to be easier to plug into a linear function than into some crazier function.
So, in the age of computers, and with computers that can handle almost any calculation you can throw at them, is there any super practical application to use the linear?
To approximations?
Mhm.
Definitely, there's lots of applications.
I can see like reducing the strain on a program if it's doing lots and lots of those calculations at
Right.
once.
If it's
but-
doing, yeah, there's lots of applications. When we're looking at tolerances, the linear approximation often is going to give you kind of a threshold, and it's going to be easier to compute. Like if you're trying to program a machine that's manufacturing something within a certain tolerance, a lot of times they'll just use the linear approximation.
Okay.
There is definitely applications. I can't think of a great one other than stuff like that. But. All right, so let's try. Oh, let's take a break. Let's take a break, and then you guys can try this one. Or if you're so bored and you don't want to take a break, you can't take a break because you're just so engaged, you can work on that one during the break. Well, the next one is really similar, so I think I'd rather pass and do the other type of application. And if we have a ton of time at the end of the class, we can come back and do this one. But it's very similar to the one we just did, so let's do this one, which has nothing to do with the one we just did.
At all.
Okay, so percent change. So we have the volume of a segment of a circular paraboloid with radius r, height h is that. So they've given us the volume of part of a paraboloid. And then we want to tweak the radius and the height, and we want to figure out how those tweakings affect the volume. So we're changing the radius and the height by a little bit. What does that do? So percent change is going to be the differential divided by the variable. So dv over v is going to be the percent change in v. So dv is sort of measuring a little bit of change, and then if you take that little bit of change and divide it by the total volume, that gives you the percent change. Similarly for r and h. So dr over r is the percent change in r, or the relative change in r, and same with h. So we're given the volume of this paraboloid. The volume is pi r squared h divided by 2. Let's just put a 1/2 out in front. And we want to figure out what dv over v is. That's what we're looking for, the percent change in volume. So dv over v. So here's what we do. So we're going to figure out what v sub r is. So we're going to figure out the partial with respect to r, the partial with respect to h. And then we're going to build the dv equation. So partial with respect to r is going to be pi r h. Partial with respect to h is going to be 1/2 pi r squared. Any issues or questions on finding those partial derivatives?
I do.
Yeah?
When we did our homework, it used something like this, and R and H were like functions, and they would change depending on where you're at. So you would have to do additional stuff with that.
Not in this one. I think I know the one you're talking about, but that's a little different than here. Here we're not thinking of R and H as functions at t or anything. So we don't have to do the chain rule. So if this said find dv dt, then what you're saying is absolutely right. Then we'd have to do a dr dt and a dh dt if r and h were functions of t. So, but not in this one. In this one, we're going to create this function. We're going to create dv. dv is going to be v sub r dr plus v sub h dh. So that's the differential in v. The differential is, when we had the x's and y's, it was f sub x dx plus f sub y dy. Okay, so now we want dv over v. So we're going to divide both sides by v. So we're going to take the v sub r, which is pi r h times dr. We're going to divide that by v, which is 1/2 pi r squared h, plus v sub h, which is 1/2 pi r squared, times dh, and then we're going to divide that by 1/2 pi r squared h. So dv over v bunch of cancellation. So dv over v, cancel out a whole bunch of stuff here. So we're ending up with, let's see, I might need to do this. So the h's go away, that r goes away with that exponent, the pi's go away. We end up with 2 dr over r. And then over here, the halves go away, the whole pi r squareds go away. So it's just dh over h. So we got that. So that is our percentage change formula. This tells us the percentage change in v relative to the percentage change in r and h. So you can see that a change in radius has more impact than a change in height. If the change in radius has a multiplier of 2 out in front of it. So if the radius is changing, that's going to have more of an effect on the volume changing than the height changing. So now let's go up here. And what did it tell us? Negative 1.5 and 2.2. So negative 1.5 and positive 2.2. So those are the percentage changes in R and H. Then our total percentage change is minus 3% plus 2.2%, which is minus 0.8%. So if the radius is a little small, the height's a little big, that's the change in volume.
That's so cool.
Yeah.
Like, it just, we got down to dr over r and dh over h, and literally
You can just plug them in.
Plug them in and evaluate.
I like
Yeah,
it.
yeah, it's pretty simple.
That's nice.
Yeah.
Yeah.
No, 'cause that's a lot to do.
So one question that some folks ask, this is built off the equation that we had a few minutes ago. Let me just write it over here. We had that dz was equal to f sub x times x minus a plus f sub y times y minus b. Let me just say one thing, because you look at this and you say, oh, how come it's dr and not x minus a? And this is kind of a theoretical thing that you can rewrite this equation in two ways. You could write this like this, or you could write this with differentials. And it doesn't matter, these are all equal. So in one variable calculus, where you've got that curve, you've got the tangent line, you've got the differential triangle right there, that's dy, this is delta y. This right here is dx, and it's also delta x. When you have independent variables, the independent differential and the independent increment are always the same. So by definition, the independent increment and differential are the same, but up here, the dependent differential is approximately equal to delta y. They're not equal. But in this case, h and r, or x and y, those are both independent variables. The only dependent variable is z. So this right here is the change in x, the change in y. Those are exact changes, but they're independent variables, so delta x and dx are the same, delta y and dy are the same. So that's why we can change it to a differential.
So if you just had some function, you could find its gradients and then just dot that with the differentials, and that's this?
Yeah.
That's the same thing?
Yeah, exactly. Right, that's the gradient right there. Yeah, that's the gradient dotted with the vector differential. That's right.
So for like this problem, like this is a paraboloid, would we, like on an exam or something, would we be doing percent change for like a cylinder or for any of the other?
It doesn't even, it would be for some object that we know the volume formula for.
Okay.
So we have to have V explicitly given so that we could do it.
Okay, so like a cylinder would be okay, but not
Yeah.
a.
A cylinder or cone or something, and I'll give you the volume formula. Yeah. Yeah, like this for volume formula, I don't think anyone knows that volume formula, right? No. But doesn't it look a lot like the volume of a cone? The volume of a cone is 1/3 pi r squared h. This is 1/2 pi r squared h. Or yeah, pi r squared h. Yeah, 1/2.
Is that for a real cone or the
The
secret
practical cone. The ice cream cone.
I'm still kind of stuck on that.
The ice cream cone, not the weird cone.
Like, is it,
not the quadrant cone.
Is it technically wrong to call a traffic cone type shape a cone?
No.
Okay.
Oh, we're just flying.
No. Yeah, we got to go to this max min stuff now. 12-8. Question. Max mins in 12.5. I'm trying. What was the title of chapter 5? Section 5?
It was the chain rule.
And they had max mins?
Yeah, I don't know, we'll talk about it.
Yeah, show me after class.
This is probably just the same thing, but in 3 dimensions.
This is the same thing as in Calc 1 you had the first derivative test, and you had the second derivative test to figure out maxes and mins. We're going to do the same thing here. And here it's a little harder. There's more going on. So books will use the word local or relative for a max or for a min, and then they'll all use absolute. So local and relative are the same, and then there's absolute. So does any of the words up there not make sense to you? Does it all look right? This low point here, a local min, means all the surrounding function values are greater than or equal to it. Local max, all surrounding function values are less than or equal to. And then the biggest of all the maxes, if there is one, is called the absolute max. The absolute lowest point is the absolute min. So for us, absolute maxes and absolute mins are z values now. Talking about a z value. And one thing that should be obvious if you look at that picture is that the tangent plane should be horizontal if there's a relative max or a relative min. Right, you're going to have a horizontal tangent plane. All right. So that first box there is describing what we mean by a local or a relative max or min. So a relative max is when the function value is less than or equal to the surrounding function values. And we have a min if the function value is greater than or equal to, the surrounding function values are greater than or equal to. Okay, so we've got to be able to find these things somehow. And one thing that should be pretty obvious is that if we have a relative max or a relative min, the partial derivatives are 0 because we have a horizontal tangent plane. So that means if you go in the positive x direction or the positive y direction, there's no vertical change, so that means f sub x and f sub y are 0. Okay, well, that's how we're going to define a critical point. So we have two possibilities for a critical point. Either both partials are 0, or one of them does not exist. So if one of them doesn't exist, it's a critical point. If both are 0, it's a critical point. So we have two types of critical points. Critical points that come from both partials being equal to 0 or from one of the partials being undefined, or maybe both.
So if one of them is equal to 0 and the other one does not exist, it's still a critical point?
Yep.
Okay.
Yep, exactly. So if they're both 0 or at least one doesn't exist, then it's a critical point. Okay, so that's how we're going to list our critical points, and then we're going to characterize them. So next thing we have to define is a saddle point. This is like an inflection point in one variable calc. So for a saddle point, every single, if you were to look, if you're going to go to the saddle point, no matter how small you write it, no matter how small you shrink a disk around a saddle point, there's going to be function values that are above and function values that are going to be below that point. So this saddle point has a z value, right? It's got a z value right there. No matter how small you zoom a disk in around that, there's going to be some z values that are going to stick above it and some that are going to stay below it. That's going to be a saddle point. If it doesn't, if for every single disk, there's always points above and points below, then it's a saddle point.
It's like a boundary point, kind of?
Not a boundary point, because boundaries are on the edges, so we're thinking of our disk centered at the saddle point. So if we take a disk and we center it at the saddle point, some function values will be above the disk and some function values will be below the disk
So it's a local max
if you
and
put it right at the saddle. So if you
okay.
put that disk right at the saddle, some points of the function will be above and some will be below.
Could you phrase that as a saddle point is where it's a maximum on one axis and then a minimum on another?
That is definitely the same idea.
Okay.
And it doesn't have to be a coordinate axis, but that is definitely the idea. Like if you have the monkey saddle, where
I don't know what that is.
the monkey saddle has three dips instead of just two, because the monkey needs a place to put its tail. So there's the feet and the tail for the monkey saddle. So it's got 3 dips instead of just 2. The monkey saddle.
And yeah, an inflection point from one variable calc, that's pretty much the point where the slope goes from positive to negative.
Did you say inflection point?
Yeah.
Concavity changes.
Yeah.
Where concavity changes, yeah. From concave down to up, right, or up to down. Changing concavity. So that's going to be one of our things. When we find our critical points and we analyze them, we could have a max, we could have a min, or we could have a saddle point. So here's our test. It's way easier than it looks. We have to find this D. That's going to discriminate our critical points. That D value will tell us whether we have a max, a min, or a saddle point. So we figure out f sub xx, f sub yy, f sub xy, plug it in, get D, and then we have all this stuff that we have to decide. Start from the bottom. D equals 0, test is inconclusive. So that means the critical point could correspond to a max, it could correspond to a min, it could correspond to a saddle point. This test is not figuring it out though. So we'd have to do something else. D less than 0. Then we have a saddle point. Let's take what Grant said and let's see if we can figure out why D would be less than 0 if we have a saddle point. So if you think about your second partials as being concavity, if you have a second partial that's negative, it means that the cross-sectional curve is concave down in that direction. So if f sub xx is negative, that means in the x direction we have a concave down cross-section trace. If f sub yy is positive, then we have concave up in the other direction. So the idea, the only way that f sub x times f sub xx times f sub yy is, so if one is positive and one is negative, that will definitely create a negative over here. Do you agree? Because that's negative already, but for D to stay negative, if both of those are opposite in sign, then the whole thing is definitely negative. So that's one way to.
Question, is that the second partial of xy times the second partial of y?
This one over here?
No, the one on the left.
Oh yeah, that's
Is that the
times.
okay.
Yeah, fxx times fyy. Yep. And so we'll definitely have a negative over there if we have concave up in one direction and concave down in the other. Definitely going to happen. Now, if D is going to be positive, The only way that can happen is if f sub xx and f sub yy have the same sign. Right? If this whole thing is going to be positive, we're subtracting off that. That means this has to dominate, which means f sub xx and f sub yy must have the same sign. So if d is positive, it doesn't really matter. Both of these are going to be negative, or both of them are going to be positive. F sub xx, f sub yy. They're just choosing to analyze f sub xx. You could, if you look at this, they're going to have the same sign no matter what. So you could call this f sub yy and f sub yy. Doesn't matter. And this just makes sense, right? If f sub xx is negative, that means you have concave down, which means a max. If the second derivative is positive, that means concave up, and you have a min. Second derivative positive, concave up, you have a min. Second derivative negative, concave down, you have a max. Second derivative negative means concave down. Second derivative positive means concave up. So the second derivative test from Calc 1, where you could look at concavity instead of tangent lines. All right, so let's try one. So we have to find all these partials. First, we need f sub x. That's going to be 6x. We need f sub y. That's minus 8y. And then we'll go to f sub xx and f sub yy. F sub xx is going to be 6. F sub yy is going to be negative 8. F sub xy is going to be 0, which is going to be the same thing as f sub yx. So now we can build our d. So d is equal to fxx multiplied by fyy subtracted fxy squared. And we're going to evaluate that d at any critical point. So let's identify our critical points before we start plugging anything in. I guess we need those first. So critical points. Critical points are where the first partials are simultaneously 0 or where one of them is undefined. Well, the partials are never undefined, the first partials. This one is 0 when x is 0. This one is 0 when y is 0. So the only critical point is where they're both simultaneously 0. And the only place where they're simultaneously 0 is the origin. Do you agree? So f sub x, set that equal to 0. The only place that's equal to 0 is when x is 0. That's the y-axis. Set this one equal to 0. The only place that's equal to 0 is when y is 0, the x-axis. So the only place where they're simultaneously 0 is the origin.
Can you explain why f x y equals 0?
So f sub xy, so we go to f sub x. If we partially differentiate this with respect to y, that's 0. Or if we come down here and partially differentiate this with respect to x.
I missed what CPS means.
Critical points.
Oh, okay.
Critical points. Critical points.
It
Critical
does.
points.
He's like a little dude.
One of those
Or
things.
podcast station.
Critical points. Just critical points, nothing more. So f sub xx at 0 is 6. F sub yy at 0 is negative 8. So we end up with negative 48, which is less than 0. So our conclusion, therefore we have a saddle point. So saddle point at 0, 0. Yeah?
So can you immediately jump from there's a negative 8 and a positive 6, like one's negative, one's positive, to saddle point?
Yeah, absolutely.
Okay.
Because the fxy has to be negative because it's squared. So yeah, it's not going to change anything. So yeah, absolutely. So if you know these are different in sign, now usually there's going to be letters in there, so it's not going to be quite as obvious as that. But I was try another one. So 16, same idea. Let's find all the partial derivatives. F sub x, 2x plus y minus 2. F sub y looks like x minus 1. F sub xx is going to be 2. F sub yy is going to be 0. And then f sub xy is going to be, f sub xy looks like 1, which is the same as f sub y x. And let's go with our critical points. Critical points, we have to set the partials equal to 0.
Why is f sub x y 1?
So f sub x is right here, and then if we partial that with respect to y, the coefficient of y is 1. Similarly, if we went to f sub y and partialed that with respect to x, we would get 1. So those will always be equal. So critical points are where the partials are 0, simultaneously 0. So let's set up a system to find our critical points. So that's our system to find the critical points. The solution for the second equation is x equals 1. We plug that into the first equation, which is going to give us y equals 0. So our only critical point is 1, 0. So then we have to figure out our discriminant at 1, 0, or for 1, 0. So f sub xx multiplied by f sub yy minus f sub xy squared. So that's going to be -1. So again, we have a saddle. So saddle point there also, but for a different reason. We didn't. Our concavity things both went away there. But as long as you end up with a negative discriminant, saddle point. All right, let's try another one. So let's plow through these partials. So we have f sub x, 4x cubed minus 4, f sub y, 4y cubed minus 32, f sub xx, 12x squared, f sub yy, 12y squared, f sub xy, 0. Any question on those? Find all those partials, and then we have to go with critical points, so we have to set up a system again. 0 equals 4x cubed minus 4, and 0 equals 4y cubed minus 32. All right, so we have to solve the system. We have to figure out where both of those are simultaneously 0. Yeah, not a lot of choice here, right? Top one, it looks like the only place that's equal to 0 is at x equals 1. And the bottom one, y equals 2. So our critical point, one critical point only, 1, 2. So then we have to figure out the discriminant at 1, 2. So f sub xx, where we plug in 1 for x, is 12. F sub yy, plug in 4 times 12, 48. Plug in 2 for y. Minus 0. We don't even need to multiply this out. All we need to know is that it's positive. Doesn't matter. As long as it's positive, we know where to go. So if it's positive, we take a look at these two guys. Those are both positive. Second partials being positive means concave up, which means we have a local min. So that is going to be a local min.
How would we know whether that's a local min or an absolute min?
Great question.
Because if that's the only critical point, then shouldn't that be the lowest point possible?
Absolutely.
So pretty much you just have to find all the critical points, test them out, and then find the max and then
So, and that sometimes works. It depends though. If you have a function that's undulating, you could have a max, a local max and a local min, but the surface could still go up and down forever. So you may not have an absolute max or an absolute min. Right?
So
So we can't tell.
Do you agree?
So we can't tell.
I guess so.
right?
So pretty much
So,
if you have
but
an
now
infinite,
here where you have only one critical point, here for sure we know that this is also an absolute min. So this is also an absolute min because there is only one of them. For the surface to turn around, there would have to be another critical point.
all right. So pretty much if you have an infinite set of critical points, then it can be difficult to tell.
Yeah, if there's an infinite number of critical points,
So if you have two
it
then.
could be very difficult to tell.
Of course, then.
Then you
But
have
if
to
you-
test both.
So yes, if you have two critical points, if you have two critical points, you would have to test both.
Okay.
Yeah. If you have
An
three.
infinite number, you have to test.
Yeah, we're not going to have an infinite number.
I don't know. What about
So
one?
let's say you had something like a sphere. Would
Yep.
you have no maxes and no mins because it's equal all the way around the surface?
So first off, we're dealing with functions, not relations.
Okay.
So we're dealing with surfaces that are functions.
Okay.
So vertical line test.
So it has to pass a vertical line test. So in Calc 1, you never were finding critical points for, totally weird squiggles, right? You're only finding critical points and analyzing maxes and mins for functions.
Okay.
So it's the same idea here. So our surfaces are all functions. They're not curling under each other, under themselves.
All right. Well, what would happen if you have a shape where pretty much it's like a wave pattern where the closer you got to the origin, the higher the amplitude. So it is kind of something like this if you took a trace of it.
Mm-hmm.
Yeah. Would it be now? Let's see.
So you can have an infinite number of maxes and mins, and if you have like a sine function, you can certainly sort of do a period type thing between them. You could do that. Yeah?
So I'm guessing we knew it was a min because the x squared means it would be positive, right?
Yes, because both of these are positive. So at this point, this is f sub x, then this is f sub y. Both those are greater than 0.
Okay.
So
So you
it's-
don't know if it's positive until you know your critical point.
We have to know our critical point first, because it's possible that these were 0, if x was 0.
Like if we were doing 12x, we would have to plug in our critical
Right,
point to
if
know
we were
it's
doing
12x.
12x, right, we would need to know what the critical point is first before we decide whether these are positive. So I usually look down here where we've plugged in our points so we know that this is f sub xx at that critical point, that's f sub y at that critical point.
So if the critical point was 0, 0, the test would be inconclusive.
So here, if the critical point was 0, 0, we would have an inconclusive test, yes. Yeah. If d is 0, we do not know. All right, let's take a look at inverse tangent of xy. So again, we'll find our partial derivatives. So f sub x, f sub y. So that's going to be partially with respect to x. We'll do our chain rule part. Partial will be inside with respect to x is y. And then we get 1 over xy squared or x squared y squared. So those are our first order partials.
Are we supposed to
Totally
know that?
forgot about that.
What's that?
Are we supposed to know that?
The derivative of inverse tangent?
I haven't done that in a long time.
Oh, yeah, 1 over 1 plus x.
We did it last semester.
It's 1 over 1 plus
Last
x
semester
squared.
for you.
It's like the easiest one to remember.
When was last? When did you take Calc 2?
Calc 2 was like a
I just
year
got
ago
lost in
or
it.
longer.
This derivative you definitely need to
As soon
know.
as you plugged in like the
So
square
yeah,
and the y
inverse
squared, mine was
tangent
like
of x, its derivative is 1 over 1 plus x squared.
It's like initial
Very
shock.
important.
It's like it's the same,
Yeah.
but it's
Is it actually 1 over 1 plus x squared, or is that one on top supposed to be like
It's
x?
No,
Well, it's
A.
just the
dx, yeah.
derivative
Oh, I
of
forgot
your
to put it
x.
in
Tan
dx,
A.
yeah.
It's just the derivative of your x, because that's
Right.
what
So
inside,
like that
right?
would be dx on top technically,
No,
right?
So this particular one has a 1x. So if it was inverse tangent of
It's just the
ax,
derivative of your,
then it would be a over 1
of
plus
what you're
squared.
taking the arctangent.
But if it's just 1x.
Yeah, that's just what I mean, is, like, you gotta keep in mind that if
Chain
x
rule.
isn't just x, then you're.
Yeah.
Yeah, then you have to chain rule it. Yeah, definitely have to chain rule it.
So you have to
Would you
divide
have
by
an
a,
ax
right?
squared on the bottom?
Yeah.
Or a
It's
squared,
a over
squared.
x,
No, it's just,
x.
Oh, sorry. Yeah, this would be 1 over, this would be ax quantity squared here. Yes. Yeah. 1 over 1 plus the inside squared. Whatever's in the parentheses. Okay, so there's our first derivative, first partial. So let's go with the second ones. So partially the upper one with respect to x. What is low partial high?
Bottom and then 0?
0, low partial high, the partial of the numerator with respect to x. We're doing f sub xx, so we're partialing this with respect to x. So f sub xx, low partial high is 0, minus high, partial low with respect to x.
2y squared.
2xy squared, all divided by the denominator squared. So that, in the numerator, we could simplify that to minus 2xy cubed squared. All right, and f sub y should be pretty darn similar. Low partial high is 0. Minus high partial low, so the only difference is that we're going to get minus 2x cubed y over 1 plus x squared y squared, all squared. So those are our mixed, or those are our second order partials. And then our mixed partial, oh gosh, let's not look at that yet. That sounds painful. Let's ignore it for now. Let's find our critical points. Let's do what we can do without causing pain. Okay, so let's set these equal to 0 to find our critical points. And when we set these equal to 0, we have a pretty nice critical point. Looks like we need to get rid of that plus. So what's the critical point? Yeah, the denominators here are always positive, so we can multiply both sides by the denominator. So we get a critical point of 0, 0. So our only critical point is 0, 0. One critical point only. All right. So can we get rid of do we have to find f sub xy?
No, because it's just 0.
But we don't know whether f sub xy is 0 or if
or
it's
something that makes it negative.
which makes it a saddle point.
We should find it.
So we need to find it.
Dang it.
I know. I feel that pain. All right, so f sub xy or f sub yx doesn't really matter.
Wait.
So
Should we multiply that, or you did the y already?
say that once again.
Oh, I was just gonna say, would it make it easier if we multiplied that y through the numerator?
But no, we're doing this one right here.
Oh.
So we're starting there. You were not starting there.
I was ready.
You were ready. She was ready.
How? No. So we just don't know if it's negative or 0, right?
Yes. Those are the only.
That's our only restriction.
So we either have a saddle point or the test is inconclusive. Those are our only choices. Now our guess, we know what the inverse tangent function looks like. We should.
No, we don't.
I feel so much better about myself now. Thank you.
It's like a
So inverse tangent looks like that.
It's just the
So we're assuming it's probably a saddle point. Okay, let's find out. So f sub xy, we're over here and we're partialing that with respect to y, and this is a pain because we have a quotient, right? There's a y in both top and bottom. So here we have to do low partial high. So there's low partial high is 1 minus high partial low. So minus y times the partial of the denominator with respect to y. Partial of the denominator with respect to y,
2x squared y.
2x squared y.
Multiply by -1.
Where's the negative one?
Yeah, the negative.
Just, is that
Yeah,
is
why
that
is
just
it a
one?
negative
That's
one?
just one, right?
So this is low, oh, why is that -1?
Yeah, that's what we were asking.
All right, low partial high is plus 1. Low partial high minus high partial low over low squared. Now we don't have to simplify this because all we're trying to do is, let's
So
just,
now we can just plug it in.
I know.
What is going on?
It's winter.
It's the wind. It's the wind outside.
It's the wind. So the discriminant at the origin is what then? So f sub xx and f sub yy. I guess I went down too low.
Wait, don't you have to square the bottom there?
Yes.
There's like hawks today.
Square the bottom. So when we find f sub xx at the origin, isn't that 0? And that's 0. So we're going to have 0 times 0 minus.
You're right.
Yeah, you get
It's just
one.
one.
Just get one.
You get 1 over 1.
So we plug in 0 here, we get 1, that goes away. 1 over 1, so we get plus 1. So we get minus 1.
So we have -1 for our discriminant.
-1 for the discriminant. And so that tells us that we have what we kind of suspected. Therefore, we have a saddle at the origin.
Oh, because this is 0.
Yeah, because that,
Saddle point at 0,
that's
0.
at the end of the equation, so it's minus that.
Regular saddle.
Because squared is just.
Not a monkey saddle. All right, any step there that you want to look at more carefully? Any step that caused you grief? Good.
So when you
That's so that's why.
shade you S1 and you put it into the you evaluate it at 0, 0.
Yes.
Okay.
So when we're evaluating at 0, 0, that's all going away.
Okay.
This whole thing's going away. That's going away.
Okay, that's
Yeah.
fine. I was
Yeah.
just like, wait, what?
Yeah. So if the
Yeah.
ordered pair for the critical point was 1, -1, we'd have to plug it all in and
Okay.
we've
That
had a
makes
lot of,
sense.
lot of saddle points. All right, let's do the hard part now. So, absolute, we talked just a smidge about it. If we have, if the entire domain is the xy plane, and there's only one critical point, that means that it's going to also correspond to an absolute max or an absolute min. There's just one. If there's one critical point that corresponds to a local min or a local max, it's going to be absolute. Now, in Calc 1, you did something called the extreme value test. Do you remember the extreme value test or the extreme value theorem?
I remember
No.
hearing it.
You remember hearing about the extreme value theorem?
I remember doing it, I don't remember.
So the extreme value theorem says that if you have a function, wow.
Please stop.
I couldn't for a second. It was like so interesting. So the extreme value theorem says that your function is defined on a closed, bounded interval. If it's defined on a closed, bounded interval, there absolutely is an absolute max and an absolute min. If you have a differentiable function on a closed, bounded interval, actually it just has to be continuous. It doesn't even have to be differentiable. But if you have a continuous function on a closed, bounded interval, there has to be an absolute max, there has to be an absolute min. Totally different than if you're on an open interval AB. So on an open interval, if we drew this same curve, there is not
An absolute.
necessarily an absolute max or an absolute min. Do you agree right over here? Let me move that B just so it's lined up a little better. And let me make that dip so it comes down below there. So it's more like the other one. Do you agree that this function has no absolute max?
Yeah.
Right? You get closer and closer and closer to that open circle, but you never get to a number that is the absolute highest y value, like you do here. There is a max, absolute max. This one does have an absolute min, but no absolute max. Okay, so if your domain is closed and bounded, you will have an absolute max and an absolute min. If your domain is open, you may or may not, depending on what's going on. So keep that in mind. So definition of absolute max just says that the function, we have a max if that z value is greater than or equal to all surrounding z values.
What about a line, a horizontal line like y equals 2?
Mm-hmm.
That's on if you put that on a bounded interval, it...
Yep. So that's the absolute max and the absolute min. That's a very boring question.
Oh.
I mean, I don't mean quite, I mean very boring function. Very boring function. Not a very boring question. It's a good question, but it's a boring function. Okay, so the absolute max is 2, the absolute min is 2.
That is a very boring question. Stop asking boring questions.
You wonder why we don't ask the questions?
Is that really your question? It's so boring. No, it's a very boring function. Very boring function. Right, so by these definitions, some older books don't include the equal to, and so they say for it to be a relative max or relative min, it's got to be strictly greater than, and so then in this case that would be different.
Yeah, that's what I was thinking.
Yeah, exactly. I knew that that's what you were thinking. And so that one, the absolute max is 2, the absolute min is 2. Yeah, it's just a
Very boring.
very boring function. Very boring function.
Very boring.
Very boring function.
Very boring.
All right, so find the absolute max and min on a closed bounded set. First, we do what we just did in the previous problems, where we find the critical points and we analyze the critical points. So that's on the inside of the domain, the interior points. Second partials test. Second partials test is only good for the inside of the domain, not the boundary. It's only good for interior points. Then we go to the boundary, and that's the hard part. All right, so, and then we compare them all. Step 3 just says compare everything. So let's try this. All right, so we've got this function. It's a function of 2 variables. It's a surface. We are going to have to find f sub x and f sub y, so let's just mindlessly do that first.
All right.
Let's go with the mindless activities first. So as long as we can do mindless activities, keep on trucking. And f sub xy, f sub yx, both 0. Okay, critical points, that's pretty mindless. We can figure out where these are both equal to 0. So the only critical point is 0, 0. And when I say only, I mean the only critical point interior to the domain. Let's draw a picture of the domain to make sure that we're visualizing our potential critical points. So we're on a disk of radius 4. We're on the inside, disk of radius 4. So the boundary is included here. But this critical point, this is a 2-variable critical point. I'm going to put a little, I guess I can write it as a point. I'll just put a dot. Yeah, that's boring. Let's use pi. Let's put a little pi
I like
in
the
there.
pie cookie.
Pi cookie.
Yeah.
Right there. So there's our critical point, pi cookie. That is the only critical point interior. We can use the second partials test to figure out what's going on there. Let's do that. Let's just analyze that point before we get to the boundary. So the discriminant at the origin is equal to f sub xx times f sub yy minus f sub xy squared. So we get 8, which is greater than 0. So what does that tell us about that critical point. That's corresponding to A.
We have a local min.
So these are both positive. So positive there and there. So the second order partials are positive, which means concave up, which means min. So we have relative min right there, or they call it local in this book. Local min. So that's what we know so far. It may be that it corresponds to an absolute min. We don't know yet. We have to keep on trucking. Yeah.
But don't we know that it does correspond to an absolute min?
If you know what the function's graph looks like, and you know that it's
Well, I mean, not even that, but you only have one critical point.
Exactly.
And since you only have one critical point, it can't shift back down.
that's true.
So
That's
then
true.
you just
That's
automatically
true.
know that's it, and just
That's true. Yeah, that's absolutely true. It's so in general, yeah, if you had more than one, the function could turn back, but because there is only one, you're absolutely right. There's no turning around. So it's got to be absolute also. That's true. So we can conclude that right now. You also can look at this function. You see that it's a paraboloid, and that origin is corresponding to that lowest point on the paraboloid, so you know that it's going to be absolute also. All right. Now, if this was an unincluded boundary, there would be no absolute max. There would be no local max if we unincluded the boundary. But we've included the boundary, so now we have to analyze the boundary. Okay, so the boundary is x squared plus y squared equals 16. That is the boundary. So what we want to do is plug the boundary into the function to turn it into a one variable function along the boundary, because then we can differentiate one variable style, prime style. So if we look at this, we can solve this for y squared. Y squared will be 16 minus x squared. So now we're going to plug this into the function. So the boundary, we have f of x, because we're turning all the y's in the equation, we're turning them all into 16 minus x squared. We're changing them. We're turning everything into x's. So the boundary z values are now given by that expression right there. So this one variable expression is now calculating the z values along the boundary. So if you are here or here, x is equal to 0, so your z value at those 2 points is
4 and negative 4.
4 negative 4.
so those are where x is equal to 0.
What
Something we plugged in something wrong.
Yeah, I think the first f of x, 2x.
F of x comma y? Is that what it's?
No, we got rid of
It's
that.
supposed to be 2x squared plus
This
16.
right here is supposed to be a plus right there.
Yeah.
That's supposed to be a plus. Because the z values better be positive, because this parabola is opening up. So we got rid of the y though, Eric, because we are trying to turn it into a one variable function, because we know how to analyze high and low points for one variable functions.
Why don't you square the y term when you put it in?
Let's see,
Y
because
squared
I
equals-
because
Y
I
squared is
solved
equal-
this.
Oh, okay.
You see it? So that is y squared right there. So we're going to
Oh, okay.
replace y squared with what it's equal to. So anywhere on the boundary z values only depend on x. So we know that at the top point and the bottom point, where x is 0, the boundary, we're going to be 16 and 16 there and there. How about where y is 0? So that is x equals 4 and x equals minus 4. So at those 2 points, what would the surface values be? 32. So at this point and this point, x is 4 and negative 4. We plug those in and we're going to get, right, x. Square both those, we get 16, add 16 to 32. All right, so but now that's a one variable function. We know how to find the high and low points. Take the derivative, set it to 0. So f prime of x is 2x. Set that equal to 0. This means that x equals 0 is a one variable critical point. Different than a 2-variable critical point. This is a 2-variable critical point. So a 2-variable critical point is an ordered pair. A 1-variable critical point is just that number. X equals 0 is a 1-variable critical point. That's going to correspond to, what's it going to correspond to? The 2 on the y-axis. So x equals 0 is a 1-variable critical point. That corresponds to which ordered pairs? So we go back up to the boundary. If x is 0, y is plus or minus 4. So 0, comma 4, 0, comma negative 4. So those are critical points for the boundary. They're boundary critical points. So let's put some pi on there. So we have those two guys. So those are the only critical points on the boundary. So now we analyze the values, the value of the function at all of these critical points. So let's analyze, let's compare. So we have f of, let's use a different color for this. We're doing something totally different now. So f of 0, 0, let's just see. And now we already talked about that we conceptually realized that this had to be an absolute min, but let's just put it in there anyway. So f of 0, 0 in our function turns into 0. And then f of 4, comma 0, 0, comma 4, I should say. F of 0, comma 4. And f of 0, comma negative 4. Both of those we said were 32. So this tells us that we have absolute min of 0, and these are both the absolute max. So absolute max of 32. So 32 is the absolute max, and 0 is the absolute min. Question? But what? You.
Yeah, pretty much. Although without plugging stuff into the original function, there's no way whether we can tell whether boundary critical point is
Max or min.
local or.
So on a boundary point, we have to take all the boundary critical points and compare them. Yeah.
How did you find where f of 0, 4 equals 32?
I'm going to put a BCP here to call those boundary critical points.
Mm-hmm.
So we're plugging those into right there, because this is the function value along the boundary, where I just need to plug in x equals
0?
Wait, where did I get 32?
I don't
Go
know.
up one more.
I got 6.
You plugged it into x squared.
Did I plug in the wrong ones?
Because if you plug that into the
X
function, you
equals
get
0.
16, right?
Wait, what am I saying here? Where did I get 32?
Go to the original function.
There it is.
No, you still,
The original
4 squared
function,
plus
you still
16.
get 16.
when we plug in 0, 4,
You still
why,
get
something's wrong.
I guess it's
Something is wrong.
The 32 is gone now, too. I don't
Yeah, the
see
32. Yeah,
anymore.
where'd the 32 go? 32 happens when we are there. These are supposed to be the critical points.
Oh boy.
Wait, what happened? Did we solve for this right? That's the boundary.
32 being gone.
Y squared equals
I know,
16 minus
I know.
x squared. Plug that
Well, I
in right
plugged it into the
there.
function.
Do we have
I
to
was
just
like,
issue
"Oh,
a
I get
retraction on this whole problem?
No. No, I'd refuse.
Okay.
Wait, why would you plug that in over to the original function? The boundary isn't necessarily the same as the function.
Yes, it is.
Well, you said what this one has
So,
x squared
so
plus
what the
y.
boundary, when we take the equation of the boundary and plug it into the original function, it gives us a way to look at the surface values just on the boundary. So on the boundary, y squared is always that. So y squared is always that. So we can plug that in up there to get our function value on the boundary. So on the boundary of the function, we really only need the x value. We could also solve this for x squared and plug it in there so that the boundary values only depended on the y coordinate. That would also work.
Okay.
But, okay, so let's see. So where partial derivative there is 0. Plugging in 0 there, we get y equals plus or minus 4. I am baffled. Let's
But you didn't even
I
write
think you might
down
have plugged
32.
in y squared for, instead of doing
Maybe
f of
that was
x
part of the
equals x
mistake,
squared
that-
plus 16,
Yeah.
you did y squared plus
The
16.
minus.
Say that once again.
I think instead of doing f of x equals x squared plus 16, what in the like tealish color,
Yep.
I think you plugged in the 4 that was the y.
Yeah.
Oh,
I think
yeah.
Yeah,
that's where you
you
made a
plugged in
mistake.
4 instead of 0 when you,
Yeah.
but you
So
never wrote
down-
it down.
So down here, so we took the do you agree with that derivative?
Yeah.
You
Yeah.
did everything
No,
right, you
everything's
never
right,
wrote it
it's just
down.
you plugged
When
it
you
back
plugged
in.
I think you plugged
When you
the
were
y value
talking,
in, not the
and you
x
plugged it in.
Okay, so we agree that x equals
Yeah.
0 is the critical point?
Yes.
Yes,
So when we plug x equals 0 in
you get 16.
right there, we get a y value of plus or minus 4, right?
Yeah.
Correct.
Mm-hmm.
You just
Uh-huh.
plugged in.
And when you
Oh, we
plugged
just
down-
plugged it into the function wrong?
Yes.
They can just set it and like.
You just said the 4 as the x
'Cause you
instead
never
of the
wrote it
4 as the
down.
y. Because you never wrote it down. Yeah.
But when we plug that point in right there, we get 16.
Yeah.
But when we plug in, this is on the boundary, right? And that's 4 comma 0. And that's giving us 32. We should be getting 32 is the
But
answer.
0 comma 4, not 4 comma 0.
I think no, you're not making sense.
Oh, really?
No, if you have, oh, I see what you're saying.
Wait,
I see
why
what
are
you're
those
saying, because then
critical
you multiply it by 2.
Yeah.
Multiply the 16 by 2. I see
Yeah,
what you're saying.
yeah.
Okay, I don't know.
What by 2?
But did
That's
you-
weird.
Did you determine?
Oh,
those
I got
points?
you. I
You
got
see
you.
it?
Those two are critical points because f of x does not exist at either of those points. It's infinite, so it's a critical point at both of those ends.
F sub x.
It makes a full 360 right there, so that's where it does not exist. Right?
This is just a paraboloid, though.
Oh.
There's no asymptotes. How is this possible? Hold on. Let's just.
Aren't our critical points 0, comma 4, not 4, comma 0?
Right. The critical point right down there that we found is 0 comma 4, but 0 comma 4 is only corresponding to 16, and 4 comma 0 is corresponding to 32. So this should be picking up that these should be the critical points.
Should it be those?
So
Shouldn't it be those are also critical points?
No.
It shouldn't be.
It should just have 2. It should just have 2. So let's see. Let's go through it again, though. So the boundary, we agree that the boundary equation is that, correct?
Yes.
You agree that we can subtract x squared from both sides? Correct. If we go up to our function, it's going to be, if we replace the y squared with that, we agree with that, right?
Maybe we have to.
And then we end up with that function. We take the derivative of that function. The derivative of that function is 2x.
We said equal.
Set it equal to 0. We get x equals 0.
Do we plug?
When x is 0, we get y is plus or minus 4. I am totally baffled.
But why would we only do that to x? 'Cause we can
Say
do
that
the
again,
sa-
Eric?
Why would we only do that to x? Because we can do the same thing to y.
It doesn't
or x
matter. It
squared.
shouldn't matter which way we go. We can solve for x squared or we can solve for y squared.
But if we solve for y squared, we get 2 separate points. That's when we would.
No, we're going to
four.
get the same points. We should get the same points. If we solve this for x squared instead, we should get the exact same ordered pairs.
Question.
Sam?
Wouldn't those two be critical points too for the boundary? Wouldn't they just be the minimum?
But they should show up then in here. So if these two were going to be critical points also, we should get in the derivative, they should show up somehow. If we're going to get all 4 of them as critical points, so you're thinking on the boundary, we've got a high point on the boundary of 32 and a low point of 16, right? So somehow those should both show up. I don't know. Let me look at it. Do you see it?
Well, I just have a question. So you're saying that you should not have that top and bottom as a critical point. You should only have the.
You may have them as critical points, but we definitely need those two as critical points also. So somehow those critical points are being lost, and I can't quite figure out why.
The slope there is infinite. So.
No, the slope's not infinite. It's just a paraboloid.
But if on the boundary it's infinite. If
Nope.
you draw a line there, it's just going straight up and down. There's no slope on that. It's infinite.
No.
You draw a tangent line,
No,
you
the
don't-
surface is a paraboloid.
But the boundary is a circle, so you can't. You you just get an infinite slope on both ends of the
No, because the paraboloid opens forever.
But I'm not talking about the parabola, I'm talking about the circle there.
But the circle, like if you look at the two-dimensional analog, if you have a paraboloid like a parabola like this, your boundary is down here. The parabola, the parabola continues on forever. But if we just look on this boundary, there is a z value for each endpoint. So there is a z value like a roller coaster for that paraboloid. So because we're on a circle and it's an elliptic paraboloid, as we, on that elliptic paraboloid, we're going to get kind of like an up-down roller coaster-y looking piece. That's what this function is supposed to represent. Let me figure, I'll stare at it for 5 minutes and figure it out.
It's like the picture in the book
and
where
I'll
they have
update
like,
it.
they have the boundary like reverse projected onto a